recording. Okay, hey Katie. Anyway, okay, so we're going to go over this one. It's just like your homework, but it does introduce another little glitch or something you have to think about that we talked about before that we didn't really discuss last time. So we're going to just, again, try to find the absolute min and max for this equation over this interval, okay? So again, first we go ahead and we get our interval of -10 and 1, right? And now I'm gonna bring back having to kind of look at the domain of the original function, right? Because remember, critical numbers are what makes it 0, but also what makes it undefined, okay? So does any number make this function undefined? No, why not, Grace? Because there's no denominators, right? So domain is all real numbers, so we're good that way, okay? Now, let's take the derivative. And we get a 1, right, for the x, plus 3 times 2/3 ends up to be just 2, right? X to the -1/3. Now, if we rewrite that, at this, now, is there a value of x that would make the derivative undefined? Yes, what would that be, Lexi? 0, right? So if x is 0, it's undefined. So x is a critical number. I mean, x equals 0 is a critical number because, again, it makes the derivative undefined, but 0 can be part of the original function. Okay? So we're going to add 0 to our number line. Okay, now, see, so I'm going to say x cannot equal 0, so 0 is a critical number. Now, the other way we find critical numbers, right, is to set it equal to 0 and solve. So how can we solve that? How can we get that x to the 1/3 by itself? Subtract 1 from both sides. So we get 2 over x to the 1/3 is equal to -1. There, yeah, multiply both sides by x to the 1/3, right? And that becomes, so those cancel, so we get 2 equals -x to the 1/3. Not yet. First, we have to make this positive. So we divide by -1. So now we get -2 equals x to the 1/3. And now, Libby, what do you think? Right, we cube it. So like if it was square root of x equals something and we want to find x, we would square it, right? Cube root of something equals x. Cube root of something equals x, so we cube it. Because again, when you've got a power to a power, you multiply. So 1/3 times 3 would give us 1. So we get x to the first over here. And what is -2 cubed? -8, awesome. So we add -8. Okay? And now we plug these in. Actually, let me also show you all an easier way. If plugging in is difficult, let me show you all an easier way that you really should be aware of on your calculator to do this. Go to your calculator. Gosh, I don't know why mine's so small. Okay. All right. Go to your calculator and graph this. Go to the y equals and graph this. Okay, it's a weird one. It has a what? Okay, so it has a cut. But plugging it in could be kind of a pain, right? But once you graph something, it fills a table with values. So you could go over to second graph, which is a table. Okay, so if we look at our table values, you can see for negative 10, you get 3.9. For negative 8, a 4. For 0, 0. And for 1, also a 4. Okay? So absolute max is what? Is at negative 8 and 1 of 4. Absolute min is at 0 of 0. Okay, does that make sense? And then again, if you looked at your graph, that should make sense, right? Again, it's hitting an absolute max way up here, but we're not going that far, right? Okay, so that makes that clear. Okay, so the one thing that you do want to remember, and honestly, and it doesn't come up very much, if you forget it on a test, it doesn't kill you. But when you're trying to find your critical numbers, you just have to remember that if there's a value that will make the derivative undefined, that doesn't make the original function undefined, that becomes a critical number. Okay, it really, and honestly, it only happens when you have fractions like this, that when you subtract one, it brings it down, right? Because on a rational function, like if your function started like this, then like negative 1 is not part of the original function, and when you take your derivative, it just becomes x plus 1 squared, so it's still not part of it. Okay, so it really only comes up when you've got, and I'll try to remind you guys as we go along when we see those. Okay. Okay, so now what we're going to look at now is instead of doing the absolute value on a closed interval where we have endpoints, we're going to talk about it at an open interval, and then we have to think about what the functions are doing all the way out to infinities. Okay, so we're going to kind of do a little review on limits at infinity. Okay, does everybody kind of remember that? No? Okay, awesome. Okay, so let's take a look. So a function that contains functions that contain a polynomial in both the numerator and the denominator, again, those are rational functions. And those are what we talked about, what we have special rules about their limits and infinity. And it actually is those same kind of rules that, if you remember, we talked about from pre-cal that tell you what the horizontal asymptote was. So quick review, if you look at the highest degree in the numerator and the denominator, and if they're equal, let's say x plus 2 over x plus 4, so they each have a degree of 1. Actually, let me change that to 3x plus 2 and 2x plus 4, okay? So the degrees are equal. So who can tell me what the limit would be? Molly. 3 over 2. Why? Where'd you get those numbers? Right, the leading coefficients, right? So it is, the official term is ratio of the leading coefficients. Hopefully that sounds familiar to everybody. All right, if the numerator is greater than the denominator, let's say it's 3x squared plus 2 over x plus 4. So what would the limit there be? Does not exist. Or infinity. Actually, it would be infinity, which does not exist. Okay? If the numerator is, the degree in the numerator is less, so let's keep this at 3x plus 2 and take this down to x squared plus 4, then the limit at infinity is 0. So if you didn't remember it as well as Molly did there, but did you all, that sounds familiar, right? You all, quick review, okay? So again, what's going to happen here is as we look at some equations, and we want to figure out what's the absolute max and absolute min, we need to know whether it's going to even have one or not without necessarily looking at the graph. Okay, so that's why we're thinking about, well, what's the limit as x approaches infinity? That'll tell us whether it's settling in on a number or whether it's going to infinity or not, right? For rational functions. Okay, so we're going to use that. We're going to practice all this here in just a second. Now, so that is for, so these rules apply for rational functions, right? Which look like this. You have a polynomial over a polynomial, right? Or you have variables in the denominator. When you're looking at just regular old polynomials, and this, I probably should have taken this. This is just the standard form for a polynomial. I'm not going to get into that, but it really just means a polynomial in standard form, such as, let's say this was 3x to the 5th plus 2x to the 4th minus, and I'm just totally making this number up to prove my point, okay? For polynomials where there is no denominator, there's no variable with denominator, the limit, as this goes to infinity, is really just however this first term performs, right? Or the end behavior of that first term. Do y'all remember end behavior? Okay. So when you're looking, and we really didn't put this when we were doing limit at infinity. We kind of did, but probably not officially. But when you want to find a limit at infinity for this, you're really just looking at this highest term. So in this example, this is an x to the 5th, right? Which if you remember end behavior, that performs just like an x to the 3rd or an x to the 1st, right? You look at the odd, and that means it's one of these. I've done this with y'all before, right? That means it's one of these. The 3 is positive, so it's one of these, okay? So therefore, the end behavior is down and then up. Does that sound familiar to you all? No. All right. Who did I teach algebra to anybody here? You all. I guarantee you all of it. Okay. Okay. Let's take a look at some examples here. So here's the deal on these. End behavior. You look at the highest degree. Okay. If it is an odd number, like 1, 3, 5, 7, 9, then it is one. I call them like Saturday Night Fever. Okay, because it's going to be one of these. Okay. If it's a positive, it's going to be down and up, just like this. Okay. So the limit of this equation as x goes to infinity is up. It's just another name, or well, I'll say up, which means it's going to positive infinity. The limit of this equation as x approaches negative infinity is down, which is negative infinity. This kind of goes along with what we were talking about earlier, where everything you learned in Algebra 2 eventually comes back in calculus, right? If we look at this equation, it is the highest term here is actually this one, right? It is odd, so it's one of these, right? It is negative, so instead of this way, it's this way, right? And the graph looks like this. So as the limit as x approaches positive infinity is down or negative infinity. You can always also look at your calculator for this. The limit as x approaches negative infinity is up, which is positive infinity. Okay? Yeah, lucky. Yeah, actually, okay, let me go to the next one, because I should have probably started with this one. If it is even, okay, like 2, 4, 6, 8, then it is acting like a parabola, right? We all know quadratics, right? We spend more time on that on these than anything. A quadratic, remember, if it's like if it's like 2x squared, then it's going to look like that, right? If it's negative 5x squared, it's going to be down, okay? So if it's even, the highest exponent of your, in the equation, if it's an even number, then all you got to think of is like a parabola. If it's a positive one, it's up, if it's a negative, down. Does that answer your question, Lexi? Sure. Okay. Let me know if it didn't. So what if it's not? Okay, so if this was 2x to the third, okay, instead of 2x squared, it's 2x to the third, it's going to be one of these. Okay? If it's positive, this one you just kind of have to memorize. A positive cubic is going like this. I think of it as like going uphill. Okay? So if it's x to the third and positive, then the end behavior is down, up. So the limit as x approaches negative infinity would be negative infinity. And the limit as x approaches positive infinity would be positive infinity.
And if it's negative 2x, it'd be up and down.
Yeah, then it would be either this. Okay? So on the even ones are easier just because you just think of a parabola, right? Positive parabola is up, negative parabola is down, down. So look at this one. So the limit is of this one, the limit as x approaches positive infinity is what? Negative infinity, right? Because it's going down. It's going down, and you don't have to write down like big girl math we normally wouldn't, but to try to relate it to algebra 2 right now I am. So the limit as x approaches negative infinity is also down, so it's also negative infinity, right? This is a even positive, so it's up, up. So as x approaches positive infinity, it is positive infinity, negative infinity, positive infinity. Okay, we're going to use this in just a second, I promise. All right, so you guys go ahead and try to do those for me real quick. Okay, so we're just going to go down the line. So Catherine, first one, x to the third minus 7x. Limit as x approaches infinity. Infinity would be this on, so it would be 4 positive infinity. There you go. Anna, what's the as it goes to negative infinity? What's it doing? Negative infinity. Okay, Jillian, negative x to the fourth. What is what's its limit as x approaches positive infinity? Negative infinity. Natalie, as it approaches negative infinity. Negative infinity because it's down, down, right? Mary Grace, as x approaches infinity for this one. Because it's up, up, right? So positive infinity. Peyton, as x approaches negative infinity. Positive infinity. Kendall, on this one, as x approaches positive infinity. Right, because it's switched, right? It's up, down. So negative infinity. And then Lexi is negative infinity. Positive infinity. Okay, makes sense? All right, now I want you all to practice this for just. Okay, so on 1 through 6, again, the limit. So check your answers. Questions about. Did you get a worksheet?
Yeah.
Okay. Questions about any of those? You guys agree with them? Okay, so again, if it's a polynomial, you think end behavior. If it's a rational function, you use our limit infinity rules. Okay? All right. Now, we're going to go back to our notes and see how we're going to use this. Okay, so again, we're still looking for the largest and smallest possible values of a function. The difference in your homework tonight is we're not going to have an interval anymore. Okay, we're looking at just all the x values. So we're still going to find the critical points. We're still going to plug them in our number line. But now we also have to think about what is the limit as x approaches positive or negative infinity. Because we need to know from the equation, is it going up, to infinity and down to infinity? What is that doing? And could that, how's it going to affect our absolute values? Okay, and it's really not too difficult if you understand the process. Of course, I guess nothing's too difficult if you understand the process. But okay, questions about that? Let's just do one. All right, so let's take a look at this. We have no interval, but let's go ahead, make a number line. What is this? What's the end behavior of this equation? 3x to the fourth. What is it doing as x approaches negative infinity and positive infinity? Up, up, right? So watch how I write this, because people tend to not do how I write it, and it makes it easier if you do how I write it.
Okay, so if the number is positive, then and the exponent is even, then it's
Up, up. It is confusing. I mean, because you're thinking even, odd, positive, negative, struggle bus, whatever. But no, you're looking at the exponent for odd or even, and then the number in front of it for positive or negative. So this is even, so it's going to act like a parabola. So it's even, it's either up, up, or down, down. It's positive, so it's up, up. Okay? Now, the way you want to think about that on your number line is, how I was putting all the x values we found over here and all the y values here? So we want to think that at positive infinity, at our x value of positive infinity, the y values are going to positive infinity. On the negative infinity, the y values are also going to positive infinity. So just from what we know now, are we going to be able to find an absolute max? No. Are we going to be able to find absolute min? Yeah. Okay? So, but writing it like this just really helps, because then in the end, when we put our critical numbers here, we can just look at all the y values and see what we can choose from. Okay? Because this is your x value. So this is saying as we go to negative infinity, our function looks like this. So it is actually, these represent the y values. So as we're going to negative infinity, our function is going to positive infinity. Okay. Does that make sense? All right. So now we take the derivative. We get 12x to the third minus 12x squared minus 12x. We can take out what? 24x. See, I get so excited I can do the math. 24x, thank you. 24x. We can take out a 12x. We're left with x squared minus x minus 2. All right. Okay. We can factor what multiplies to negative 2 adds to negative 1. That's 2x plus 1. So what are our critical numbers? 0, negative 1, 2. Everybody agree with that? Yeah, am I going too fast? Okay. Actually, I'm going to be here for a little while. Okay, so now we have, we have critical numbers of negative 1. I'm going to put them in order, 0, and positive 2. So there's a little enthusiasm. Yeah. Okay, I'm sure that's how it was meant. Okay, so now, so do you understand? These are all of our x values possible, right? Up here we're going to put our y values. How do we find our y values? Plug in the original equation, or what's our other option we don't have to do now? Graph and look at table function. You all like that one better? Let's practice that a little bit. So go into your table function. And why does it go so small? And plug that in. So 3x to the 4th minus 4x to the 3rd minus 12x squared plus 2. And I can't even read that. Okay. All right, so then when we go to y to second table, and we're looking for -1, and I can't, honestly, girls, I can't read that. So what's the -1 value? -3. 0 is 2. 2 is, what's that, -13? Okay, so again, now that's why I like the way, that's why I tell you to write it like this, because now these are all your, where it might be happening, and this is all your y values. So we're looking for, first let's look at absolute max. Do we have an absolute max? Well, the highest numbers we have now are positive infinity, right? So we have no absolute max, we have an absolute min. Where? What's the lowest y value up here? -30. So we have no absolute max because of these, and we have an absolute min at 2 of -30. What's that? No, it's because, again, we're only looking at the lowest and highest of the numbers above the line. So nothing can be higher than positive infinity. So there's no max. So then we want to look at what's less than that, or what's the lowest number up here. In other words, actually, now that we put on your calculator, if you look at your graph, look at what it's doing. It's going up here and it's slipping, right? So we've just found the point that it's getting down to -30 there. Okay? All right, let's try another one. Okay, so we've got this one. Let's think about our number line. What is the end behavior for this one? 0, right? Because it's a rational function. The exponent on the numerator is less than exponent on the denominator. So on our number line, what we're going to say is as x goes to positive infinity, this goes to 0. And as x goes to negative infinity, this goes to 0. Okay? So the zeros are going to be options. If we find all of our critical numbers and they're all negatives, right, let's say, then our absolute max is happening at positive and negative infinity. It could be a thing. You know, that might be the highest value we get. If these are all positive numbers, then this might be our mins. Because again, we're going to look at all the y values we find and pick the highest or the lowest. Because this, the limits of infinity, if we were to graph this, as x goes to infinity, this has a horizontal asymptote. So it looks something like, I don't know offhand what this looks like, but it's looking like something like this. Right, because this is actually the first, and this is actually the second.
Oh.
2 is greater than 1. Yeah. I put zeros because the answer to this is the limit as x approaches infinity here. For this function equals 0. Okay? So now we have to see what our other options are. Okay? And we do that by taking the derivative. So derivative of the top is 1 times the bottom minus derivative of the bottom times the top all over the bottom squared. Now, again, we could look at what makes this undefined, right? But whatever makes this undefined is also going to make the derivative undefined, so we don't cancel each other out there. Okay, so now if we clean that up, we get x squared plus 1 minus 2x squared all over x squared plus 1 squared. That simplifies to what? Negative x squared plus 1 over x squared plus 1 squared. That's not at all confusing. Is that good? Now what are we going to do? Set equal to 0 and multiply by the denominator, right? If y'all don't mind, I'm just going to show that like this. Does everybody know what I'm doing there? Okay. And then these cancel. What is 0 times something to the second? 0. Now what do I do? Minus 1. We get negative x squared equals negative 1. Divide by negative 1. X squared equals positive 1. It's very easy. You'll know exactly what you're doing. So x equals plus or minus 1. So we come up here. What'd you say? You understand it? They don't call it calculus for nothing. Okay. I don't know why they call it calculus, but anyway, it's not easy. I should look up what the word calculus means. All right, anyway, so now we have to find, now what do we do? Plug it in. And we can do this in our heads, right? So, I mean, kind of. You should be able to. All right, so f of negative 1 is going to be negative 1 over negative 1 squared is positive 1, right? So 1 plus 1 is 2. So up at negative 1, up with the y values, I'm going to put negative 1/2. On your calculator, you got 0 for negative. Let me see how you plugged it in. Okay. Yeah, when you're plugging this in on your calculator, you want to do this. Because if you don't, then you're only dividing x by x squared and then adding 1. Okay? All right, so now if we plug in positive 1, we get 1 over 2, right? 1 over, so we get positive 1/2. Okay, so now when we want to find min and max, we only look at our y values. What's the highest y value we have here? 1/2 at, what's the lowest one? At negative 1. So our absolute max is at 1 of 1/2. Our absolute min is at negative 1 of negative 1/2. If like if this had also been a negative, then our max would be at the ends, right? Positive and negative infinity would be our maxes would be happening there of 0. So let me write that down. So we have an absolute max. Is that at positive 1/2? Positive 1/2 of 1. an absolute min at negative 1/2 of, oh, am I doing that right? Yeah, I'm doing, okay, sorry. It's at 1. It's max at 1 of positive 1/2, right? And then at negative 1 of negative 1/2. Okay, questions about that? Very good. I know this is exciting. No, just stay awake for me, okay? All right, now let's try another one. This is another little kind of a twist that you might, okay. So this is not quite an open interval, but kind of open, right? Because here, we're not saying all of negative infinity and positive infinity. We're only saying x greater than -5. So when we draw a number line, we really, we're going to have -5 at this end, and then we're going to stop. Can I think of why I would do that on this problem? Right, but why would I put this interval on this problem? If this was an open interval, would we have any mins or maxes? What's that? If I just had this as an open interval, okay? If I just said no numbers, what's the end behavior on this? Down, up. So would there be any mins and maxes? Would there be any work we could do? No. So you won't see many of these, but you might see one. And so if I didn't have an interval on here, it looks like this, or it looks like the other one. If I didn't put an interval at all, then that function would look like this. And we could say there's no absolute maxes at all. Is that? Yes. Well, you just have to identify, you have to recognize it. Okay. On this one? Well, so here, no. So let's look at this. So we still need to. So what is end behavior on this? As x goes to positive infinity, what does the value? It goes up, right? We don't need the limit at negative infinity. So we just know at positive infinity, it's positive infinity. So we know we're not going to find a max, but we still need to find a min because that's cut it off right here. Okay? Right, because I stopped it at -5. All right, so take the derivative. Let's kind of motor through this. So take the derivative. We get 3x squared plus 6x. Set it equal to 0. Take out the 3x, and we get x plus 2. Is that right? Y'all checking me here when I go past that? And so we get x equals 0 and -2. I know x at 0 is going to be 7. Can somebody tell me what the other two are? Grace, just you, because I can't hear everybody. Okay. Okay, again, you could have plugged those in or you could have graphed it, right? It just takes some time. So now when it comes to absolute values, we're looking up here for the highest or lowest value that our function is hitting. What's the absolute max? Do we have an absolute max? Because of this, right? What is the absolute min? At -5 of -43. I think so. Perfect timing there.